chapter 3. So chapter 3, what we're dealing with is psychometrics. So psychometrics. What are psychometrics? Psychometrics is simply the study of both of humid air, so both air and water vapor together. And this chapter is basically going to be split into 3 parts. First part is we're going to be looking at psychometric properties, and then eventually we're going to be getting into processes and cycles. So to start off, I'm just going to go over what the psychometric properties are. And at first, it starts with pressure. So pressure is just basically what we're used to dealing with, right? Where you have some sort of atmospheric pressure. Now, the pressure can be split into 2 different types of pressure. We have the dry air pressure and the water vapor pressure. Combined together makes for the total atmospheric pressure. So we'll come back to that. Next one is dry bulb temperature. So if you think about dry bulb temperature, it's the temperature that we're used to when we look at our weather apps or if we look at a thermometer. Basically, it's if you can think of a plastic mercury thermometer, when the bulb is dry and it gives you temperature, that's the dry bulb temperature. And the other form of temperature that we'll be dealing with, I'll be introducing this property a little bit later, but it's called wet bulb temperature. And it's simply the temperature measured by that same mercury thermometer, but with the bulb having like a wet wick on it. And this temperature, the wet bulb temperature, is a temperature value that's useful in trying to determine humidity. And again, we'll be coming back to that at a later time. Next one is specific volume. So this specific volume is actually the specific volume of the dry air. So we're talking about that we're dealing with psychometrics, we're dealing with humid air. So humid air is a combination of both dry air and water vapor. So if we take that dry air component of the humid air and we just concentrate on that, just concentrate on the dry air, that specific volume is the specific volume of dry air. Next is enthalpy. Much like what we did in thermodynamics, this is just a property that helps to quantify energy transfer terms. But the trick in psychometrics is that it's the enthalpy of the humid air per pound of dry air. So if you think about it, it's like the enthalpy of dry air plus the enthalpy of water vapor, that divided by the mass of dry air. So it's the total enthalpy of the humid air per pound of dry air. Again, we're going to come back to that at a later time. So both of these properties are specific properties, and they are per pound of dry air. And then the last 2 properties that we're dealing with are the 2 humidity properties. One is relative humidity. And we dealt with relative humidity, or I talked about relative humidity earlier, where relative humidity is the amount of water vapor in the air divided by the amount of water vapor the air can hold at saturation. So since the amount of water vapor that the air can hold at saturation, that changes the temperature, relative humidity can change just by changing temperature, even if the water content in the air stays the same. And then the last property is specific humidity. Specific humidity is basically the total mass of water vapor in the air divided by the mass of dry air. It is a direct measurement of humidity independent of temperature, right? We're going to come back to that at a later time. This is what's called a psychometric chart. Psychometric chart is a way to plot all of the psychometric properties together in a way to monitor how the properties change during a specific psychometric process. So if we look closely at this psychometric chart, normally in person in class, I would hand out a hard copy of this. But if we were to take a look, we have first on the x-axis, let's take a look at that. The x-axis gives us temperature, dry bulb temperature. So 0 degrees Celsius, 10 degrees, 20, 30, 40, up to 50. The y-axis, these values here, is the specific humidity. So this would be the specific humidity, the mass of water vapor in grams per mass of water vapor in kilograms. So actually, if you divide this by 1,000, this would be the specific humidity. So 0.026, 0.024, 0.022 kilograms of dry water vapor per pound of dry air. So this is the x, this is the y-axis, so the horizontal lines. And then we have the relative humidity lines, right? So relative humidity lines are 10, 20, then 30, 40, 50, all the way to 100%, which is saturation right here, right? So you can see, for example, this line here is what we would call the 50% humidity line. A few others that we're going to be dealing with is enthalpy. Enthalpy here, these values have these lines that kind of go across the table. Those are enthalpy lines. And then wet bulb temperature, you can kind of see in here, this is 30 degrees, this is 25. These lighter colored lines, these solid lines are enthalpy lines, but these lighter colored lines, which almost look like they're parallel to the enthalpy lines, although they're not, they are wet bulb temperature. There's a protractor over here that we're going to deal with a little bit later in the chapter. It helps to kind of quantify, sort of lay out the condition lines for humidification processes, as well as being able to use certain factors that we're going to be looking at in order to get the angle of different condition lines depending on what's happening. But what we're going to concentrate now on is just the psychometric chart itself. All right, so what I'm going to do now is I'm just going to take some time and I'm going to take us through and introduce each of the properties, making sure again that I lay out what their definitions are and be sure that we understand how they work and where they come from. First thing I want to do is just reintroduce the ideal gas law. So if you remember, the ideal gas law is telling me that pressure and volume times volume equals mass times gas constant times temperature. Or if I divide through by mass, I get P nu equals RT. In addition to that, if you remember, there's two ways to look at the gas constant. We have the universal gas constant, in metric units, and there's also a version in English units. All right, so that's the universal gas constant, but the gas constant for air, which is specific to air. Remember, universal gas constant is one gas constant that's valid across all ideal gases. But then the gas constant tells us that each individual gas has a different gas constant, which is in per mass terms, whereas the universal gas constant is in molar terms. All right, so that's the ideal gas law. We're going to be using the ideal gas law pretty significantly. Now, let's go back to pressure. Remember, we talked about pressure, my total atmospheric pressure. If I were to think about pressure and atmospheric pressure for humid air, it's a combination of both air pressure and vapor pressure. Now, the vapor pressure is going to be really low compared to the air pressure, but it is the energy that the water carries with it in the air that makes the water vapor pressure important. All right, first thing I'm going to do, first property is going to introduce is the first property we're going to introduce is going to be relative humidity. RH, it's called relative humidity. Relative humidity is a ratio of the actual water vapor mass in the air divided by saturated water vapor mass. So that would be mass of the vapor divided by what the mass of vapor would be at saturation. This is equation 311 in your book. But the thing is that I don't have a scale sitting in a room that can measure directly what the mass of the water vapor is in the air. So what we need to do is convert that into a measurable quantity. And we can do that pretty easily using the ideal gas law. So we have the vapor pressure times volume equals the mass of vapor times the gas constant of vapor times temperature, which is going to be the dry bulb temperature. Remember, dry bulb temperature is just the normal temperature that you guys are used to. So if you look at that, we can change this equation into a form that is dependent on measurable quantities. So if I go ahead and substitute the ideal gas law, so if I get the ideal gas law for the numerator, I get the actual vapor pressure times volume divided by the gas constant times dry bulb. That divided by the vapor pressure at saturation, which is what would be at saturate, right? If the air is saturated with water vapor, it would be the saturated water pressure times volume divided by R times temperature. Now, all these factors cancel out. Volume, gas constant, temperature. To give you the ratio that the relative humidity can be quantified pretty simply as the current vapor pressure divided by what the vapor pressure would be if it were saturated at that same dry bulb temperature. That is equation number 1, along with the definition of what relative humidity is. All right, so that's relative humidity. The next one we're going to look at is specific humidity. Another way to say specific humidity is humidity ratio. And here's what it is. The definition is simply the mass of water vapor divided by the mass of dry air. Or mass of vapor over mass of air. Now, something to understand. In psychometrics, the basis for all specific properties, remember what specific properties mean in thermodynamics. The term specific properties means that it's per mass. So the basis for all specific property, sorry, I should probably make that plural. The basis for all specific properties in psychometrics is the mass of dry air. It's per mass of dry air. The basis for all specific properties in psychometrics is per mass of dry air. That's why the specific humidity ratio is very important. I'll come back to that at a later time. For now, let's go ahead and try to quantify this, right? Again, I don't have a mass balance to measure mass of vapor, mass of air. So I am going to use my ideal gas law for water vapor. And I'm going to use the ideal gas law for vapor, or I'm sorry, for air, for dry air. I do that, right? Go ahead and substitute mass in the ideal gas law. Get the following. So dry bulb temperature cancels out, volume cancels out, and what I'm left with is the gas constant for air over the gas constant for vapor multiplied by pressure, vapor pressure over dry air pressure. So if I take that further, I can go ahead and substitute in the fact that the gas constant equals the universal gas constant divided by molarity. So if I make these substitutions into there, the universal gas constant would cancel out. I'm left with molarity of vapor over molarity of air times vapor pressure over air pressure. I make another substitution knowing that my ambient pressure is equal to air pressure plus water vapor, right? So I make that substitution there and I get my final form of the equation where it's 18 over 29 times vapor pressure over ambient minus vapor, which is the final form of one of what will be two equations for computing the specific humidity. Right, so if I were to switch to the next slide and go ahead and write it out in decimal point, 0.622 times vapor pressure over atmospheric minus vapor. And this is equation 3-14b from your book. All right, so that is specific humidity. So we've done two properties, well, more like three, because temperature I didn't really derive. We just kind of understood the temperature is dry bulb temperature is normal temperature. But we really went over relative humidity and specific humidity. All right. We have one more property that I'm going to introduce. And I know this video, you're going to have to watch certain parts of this again because some of this stuff can be a little confusing at first. But I'm telling you, once we get going, it's not too bad. But it is a little murky when we get started. Last one I'm going to cover today, enthalpy. So I talked about earlier that the basis of all calculations for any sort of specific property in psychometrics is mass of dry air. And the enthalpy of the mixture, meaning humid air is a mixture of dry air and water vapor. The enthalpy of the mixture is the enthalpy of the dry air plus the enthalpy of the accompanying water normalized per mass of dry air. Here's how it works. Let's say that the holistic enthalpy, right, this is all in energy terms, is equal to the enthalpy of air plus the enthalpy of vapor. If I want to put it in specific terms, I'd say, okay, well, that is equal to the mass of air times the specific enthalpy of air plus the mass of vapor times the specific enthalpy of the vapor, right? So if I rewrite that equation, I get the total enthalpy of the humid air is the mass of air times the specific enthalpy of dry air plus the mass of vapor times the specific humidity of vapor. Here's the trick I'm going to do. I am going to divide by mass of air, right? So that gets me H over mass of air equals mass of air over mass of air times H of air plus mass of vapor over mass of air times H of vapor. This obviously crosses out to 1. And if we look back, what property is this? This property is specific humidity. And this value here, the total enthalpy of the dry air plus the water vapor, this H, is the total enthalpy of the humid air divided by mass of dry air. So the final form of the equation is enthalpy, cross out that little A. Total enthalpy is equal to the enthalpy of air plus omega times the enthalpy of vapor, which is equation 317. And again, this is enthalpy of the humid air per mass of dry air. All right, I think that about does it for today. The next thing is an example problem, but I am going to wait until I'm back in class for that. So, guys, thank you so much for your attention, and I hope you all have a good weekend.